Okay, I'm continuing to work on my physics of Lagrange points. So I originally started off doing Lagrange points, and I think I made a mistake, so I'm starting over from scratch. And this is what I've done so far. So the first thing to do is to take two generic objects orbiting each other, and then I can use that to find the Lagrange points. And this way I can do it for any masses. I want to be able to do it for binary stars or the Earth and the Sun or whatever you want to do. So the first thing I did was to find the conditions for a binary star or two objects, doesn't matter, such that they're in stable circular orbits. Now, in order to do that, you have to find the center mass for these two masses. This is M1, M2. You also have to find the velocity such that they have the same angular velocity, and this rotates around. And then I actually modeled this. Let me switch over here and show you that there's actually already a model of that. And there will be a link down below to the video to show you how this works. Okay, so here is the code. And let me just run this. There's nothing super magic about this, but you can see that the two objects orbiting, and you can put the masses at whatever you want, and also the distance between them. And that's not running in real time because that would be weird. So there you go. So I'm going to take that, and what I want to do is to go over here and find the locations of the Lagrange points L1 and L2. So let's see. How about a red marker would be nice. So just a quick review. The Lagrange points are places where you could put a mass, a small mass, and by small meaning that it doesn't affect the motion of these two objects. Okay, so it's not a planet, it's just like a spacecraft. But as these two things rotate around with some constant angular velocity, that one is moving with the same angular velocity. So it will also be moving this way. Not the same speed, the same angular velocity, but that means that as this rotates around, that object will stay in the same position relative to that mass, and that's a Lagrange point. And this is the L1 Lagrange point. The other one over here on this side is L2. And so those are two. There's actually 5 Lagrange points, but I'm just going to focus on these two. So we're going to calculate those. It's not trivial, so it's easy to set up. It's not trivial. But here's what I have from before. So if I have an arbitrary mass M1 and M2 separated by a distance r, and they're in a circular orbit around the center mass, so the total momentum is 0 of the system. Then I can find R1 is the distance from the center mass to mass 1. R2 is from center mass to M2. V1 is the velocity, the magnitude of the velocity for that mass, and v2 is the magnitude of the velocity for this one. So they're going opposite directions initially. Okay, and then we also want to do the angular velocity. That's super important because the Lagrange point is moving with the same angular velocity as everything else, not the same velocity. So the angular velocity for mass 1 is just v1 over r1. That's the definition of angular velocity, and v2 also. So you can use either one of those to find the angular velocity, but you get that expression right there. Okay, so let's start with point L1. And just to make things simple, I'm going to call that the positive x-axis. And I don't know why I always draw my Lagrange point on that side. It's just what I do. I always think of the Earth as on the left-hand side of the sun. I don't know what it is. Maybe that's the way the books draw it. I really don't know, but I did it. So in this case, if I draw a mass right there, okay, there's my mass at the point Lagrange point L1. There are two forces acting on it. There's a gravitational force this way. I'll call that F1. That's a gravitational force on the mass, and this just has some mass m, due to the object M1. And then there's a backwards pulling force this way due to mass 2, F2. And I can say F net equals ma. But if I write that as just a magnitude, then I know that this is the sum of the forces in the x direction, and the acceleration is centripetal acceleration because it's moving in a circle. Okay, so let's just start putting it all together, and then we can solve it. So if I need to find the gravitational force due to F1, it's going to be, remember, the gravitational force in general, the magnitude, I'll call it Fg, is g m1 m2 over r squared, where g is the gravitational constant. That's the product of their masses, and that's the distance between them squared. So I need the distance from here to there. Let's call this RL1. It's the orbital radius of mass, the Lagrange point 1. So if that's the case, I can write the gravitational force due to F1 is going to be equal to G M1 M over this distance squared. So this from here to there is R1, from here to there is RL1. So it's going to be R1 plus RL1 quantity squared. Now I need to do the same thing for F2. Here's this point. So it's going to be minus G M2M, and it's minus because that's in the negative x direction, divided by the distance. So this is RL1, and this is R2. So I need to take the difference in those. So it's going to be R2 minus RL1 quantity squared, and that's my net force. So that's going to be equal to the mass times acceleration, and centripetal acceleration is v squared over r, or omega squared times r. I'm going to use the omega squared r. So it's going to be the mass of my object there, m. Omega squared, I can use this whole thing, right? Because that's my omega, so I'm going to put in this g m2 over r squared r1. And then I need to multiply that by r. So what's the radius of the circular orbit for L1? It's RL1. So RL1. Okay, so that's my equation. Now, just think about this, right? G is a constant. First of all, I'm going to cancel all the m's. But I'm not going to cancel the g's. Okay, I'm not going to cancel the g's just because it makes the units work out a little bit better. We can talk about accelerations. This is the acceleration due to the force, and this is the result of the acceleration. So the only thing I don't really know is I can find R1, R2 based on this. I'm not going to put this in, right? I don't really care. I don't know RL1, RL1, but you see I have RL1 in here multiple times, and it really is going to be kind of difficult to solve since these are squared and on the denominator. So what we're going to do, what I'm going to do, is to set up a binary system, and then I'm going to call this left-hand side and call this right-hand side. And what I'm going to do is to change, oops, you can't even see that. I'm going to change the value of RL1 until these are the same, because I can't solve it. So I'm actually just going to, what I'm actually going to do is plot this and plot that and see where they intersect as a function of RL1. I know that seems kind of silly. It's a little silly, I'll admit. Okay, let's see. I want to, okay, let's just see if I can get into this. I feel like I'm going to make a mistake, but okay. Let's just do this one, and then we'll do Lagrange point, the second Lagrange point. So I'm going to switch over to the computer, and over here I do have my program already running, and I'm going to copy this because I'm going to use the same values. So I've actually already copied this. It's already a copy of that, and I don't want to really model the motion of it right now. I just want all that stuff there. I started to, actually this is all wrong. I started to make a function for this, and it was a failure. And so I actually stopped. So let's just delete that, and let's just comment out all this stuff. I don't want to really model it just right now. I just want to find the stuff. Okay, let's just run it and make sure things are working. I don't know that they will be, because sometimes, okay, so there, I got my stuff. Okay, so I picked R. This is all starting from the gravitational constant G. I'm going to make this a little bigger. The gravitational constant G, M1 and M2, which I just arbitrarily picked, and they're star-like things. And then R is the distance between them, again, star-like. The 1 AU is the distance from the Earth to the Sun, 1.5 times 10 to the 11th. You can change these up. Okay, it should work for anything. Okay, so what I want to do is to calculate the left-hand side and the right-hand side. I don't need that right now. So let's just write this out. Left-hand side equals. Actually, let me think for a second, because I'm going to go ahead and plot it. So let's pick a starting value for RL1. And let's see, if I look over here, switching back to the paper, is it possible if RL1 is 0? I want to make sure I don't miss over the Lagrange point. What if I start at RL1 is equal to 0? Then this term would be okay. This term would be okay. This term, everything would be okay. So I can do both. I'm going to start at RL1 is equal to 0. That's what I'm going to do. I just want to make sure I'm not dividing by. And I could rearrange that whole expression to make it a little bit better, but I don't really care. Oh, I'm going to get back over here. So 0. Now, what I'm going to do is increase the value of RL1. So let's just take the distance of between star 1 and star 2 as the value r. And I'm going to say dr is the step size, because I'm going to increase the value of r. And let's divide that by 1,000. So r divided by 1,000. And I don't think that's big enough. I mean, that's too big, but let's just leave it. Okay, now what I'm going to do is to make a graph. So let's go ahead and say G1 equals graph. X title equals, let's call it G. This actually is gravitational field. No, that's going to be RL1 versus Y title equal to G. And let's say the width is 500, the height is 350, because that way it'll look better. Now I'm going to need a function to plot. Let's see, let's scroll this whole thing up because you don't need to see all that stuff. So let's say F left, the left-hand side, is G curve, and we'll make that blue. Color equals color dot blue, and let's give it a label. Label equals left-hand side, and then FR. And you got to, when you say it, when it's capitalized, you say R. You got to do that, or Python doesn't work if you don't do this. I'm just kidding. I like to do it though. So G curve, curve, color equals color dot red, label equals right hand side. Okay. Now, while RL1 is less than, how far do I want to go? I mean, I guess I could go all the, I can't actually go to all the way to value R2 because I have R2 minus R1. So let's just say, we can change this. Let's say while RL1 is less than 0.9 times R2, right? Because I can't get all the way to R2, it'll blow up. So I'm going to almost go there. So now what I need to do is calculate the left-hand side. So left-hand side, I'm looking at my equation right here. See, I got the paper. See, and I'm just going to type that equation for the left-hand side. I already have G. I'm leaving G in there. G times M1 divided by R1 plus RL1. See, you notice I did that again. I really do. I don't know why I do that. Okay, minus G times M2 divided by R2 minus RL1. I'm going to stop. Okay, squared. That's the left-hand side. Now the right-hand side is going to be equal to G times M2 times RL1. See, I tried to do it nicely. Divided by parentheses R squared. I'm going to actually do this way. R1 times R squared. I always get scared when I put the order of operations like that. I don't know why. Okay, so now I'm going to plot both of those. So FL dot plot. If I don't remember to include my graphing tutorial down below, then leave a comment and I will do that for you. I mean, I have a whole bunch of stuff. I always just forget to use it. Okay, so I'm going to plot my x coordinate is going to be RL1 and my y coordinate is going to be left-hand side. My FR dot plot RL1 right-hand side. Now what I need to do is to increase my value of RL1. RL1 equals RL1 plus DR. And then that should work. Maybe. I should save it, shouldn't I? Let's see. Let's change the name. Calculating L1 Lagrange points, L1 and L2. Save. Okay, here we go. Oh, I think it worked. Look, it worked. Okay, so that really worked. And you can see here where they cross, where the two sides are equal or where they cross right here. You'll also notice something very important. it starts off with a small r, and then it goes down to a larger, it goes up to a larger and larger r. Then during that time, the left-hand side is greater than the right-hand side. The right-hand side is tiny. Should it be tiny? Well, let's just do this. That seems weird. Let's go to, look at the 5.5 times 10 to the 9th. Let's just change this. 5.5 E9. Okay, it is changing. Great. So, and there you can see a better value for that. But what I'm going to do is now make a function. I'm going to make a function since I can see that the left-hand side is greater than the right-hand side. I'm going to run this until I get to this part where the left-hand side is less than the right-hand side, and then that would be my value. And that's really a little crude, but I don't really care. I'm going to do it anyway. Okay, so let's make a function. So I'm going to say def L1. This is calculating L1. And I need to input my values for my system, which are my mass 1, mass 2, and my radius. So I'm just going to say R, M1, M2. And yes, theoretically, you shouldn't use global variables like this. This is a bad idea. I'm a bad person for doing this. But for me, it makes me feel more comfortable because I don't have to make up new names for these things temporarily. And I'm a physicist, not a programmer. So you can do bad things too. Try it. You should. Okay, so I already have those values, RL1, RL2. What I need to do is I need to do what I did right here. So I'm going to say RL1 equals 0. dr is r divided by 1e4. I'm going to actually do 10,000 points. And then I need to do this. See, now I can do this. I can copy this. I don't have to retype them because I use the same variables. Aha. See? Okay, then I'm going to say if left-hand side is less than right-hand side, then end the function and return RL1. Else, I always like to yell, don't I? Do I have to do else or can I just do nothing? Well, let's say else RL1 equals no. I think if it returns, it'll just return. I probably should do else. Let's just try that. Else RL1 equals RL1 plus dr. Okay, and then let's say I never get a function. Oh wait, I missed a step. Okay. While RL1 less than 0. Let's put 0.999. I'm not plotting it. It doesn't really matter how big it gets. Times R2, then do this following stuff. So calculate left-hand side, calculate right-hand side, see if it's greater. If it's not, increase. See, but then if it is, it should return. I guess I could just put this. Oops. This will definitely break it. RL1 equals 2 times R2. Then it won't be less than. It'll stop. I don't know what I'm doing here. Okay. And then at the end, if I get out of the loop and I don't have something, then I'll just return 0. Okay. So let's try that. Let's print L1, R, M1, M2. I know what the answer should be. I just looked at the thing. We can check. Okay, so let's run this and see if it works. I'm a little scared. Okay, so it did print it out. If I go over here, I get 4.74 times 10 to the 9th. Okay, so I get about the same thing. So I'm pretty happy with that answer. So I've calculated the point. I have a function to calculate the location of Lagrange point L1. That's good. Okay. So let's just get rid of this stuff now. I don't want to plot any things anymore. We'll come back to that when we do L2. How long is this? 19? Okay. So I have that function. Now I can go back down here, and then what I want to do is model the motion of this planet, this mass in there. So let's just turn this stuff back on and make sure everything's working. Okay, and then I'm going to run it just to check. Okay, so that looks good. So now I'm going to add an object L1. Let's just call it, I can't call it L1, and it has to be after this function down here. So let's just call that ML1. Does that look okay? Mass L1? I think that's okay. I was going to call it a ball, but then we ball all. Okay. Let's call it ball 1 for Lagrange point 1. It's going to be a sphere. The position is going to be equal to vector L1 R M1 M2, right? Because I'm going to need to calculate the location of that point, and it's going to call that function right there. And then the 0, 0. Now the radius is going to be equal to, let's see, what was the radius of the other stuff? R over 30. Let's do R over 60. I'm just picking that. R divided by 60. And let's say make trail equals true. Let's just run that and see what happens. Okay, so there's my Lagrange point right there. And you'll notice that something happened that I didn't expect. It's inside the first orbit. That's weird. I would have thought. Well, let's just let's just change those masses and see what happens. So here I have, they're 2 and 3. So let me make this less massive. Let's say 10 to the 29th. Run it. Okay, I think I want to do this one. And there's my Lagrange point. Okay, I feel better. Okay, so now what I need to do is in my loop, I need to calculate the gravitational force on ball 1. So that means I need to find the vector R11 from star 1 to star 2, to the point, and then from star 2 to the other point, so I can calculate the forces. I'm going to leave this stuff as it is, but I'm going to go up here and say R11 is the ball1.pos minus star1.pos. So that's the vector from star 1 to ball 1. R12 is equal to ball1.pos minus star2.pos. So 2, 1? Is it 1, 2? Which will make more sense. 1 on 2. R from 1 to 2. That's fine. Just keep it. Okay. So now I can calculate 2 more forces. So it's going to be F11 is going to be negative G times M1 times M. Oops. Don't have M. So let's say ball 1 dot M equals 1,000. I do need the momentum too, right? So do I have omega up here? Let's just do that. I thought I did. Okay. So omega is equal to V2 divided by R2. Right? I said that before. So down here, I need the momentum. Ball 1 dot P equals ball 1 dot M times vector. So it's going to be moving in the negative y direction. So it'll be 0 and then omega times ball 1 dot POS dot X. Right? Because that's the X coordinate is the value of L1 or RL1 and then 0. So now it does have momentum. It has to start moving with the right angular velocity, and that'd give it the right angular velocity. Okay, where was I? Times ball 1 dot M times norm R11 divided by mag R11 squared. And then I need to say the force from the other star. I can just copy this. I don't have to retype it. And it's going to be just 1, 2, 1, 2. This is going to be mass 2. And then I need the name 1, 2. Okay, so now I update the momentum of star 1, star 2. I can update the momentum of the ball. Ball 1 dot P equals ball 1 dot P plus F11 plus F12 times dt. And then I need to update the position. Ball 1 dot POS equals ball 1 dot POS plus ball1.p times dt divided by ball1.m. Boom! Okay, if this works, I'm going to be kind of surprised. Because, you know, you make mistakes, right? Okay, so scroll up here, save the thing, and run it. Whoops. I know I did wrong. Although it is kind of cool. Time step seems too big. So let's make the time step smaller. But here's what I did. I made that in the positive x. I already said it was supposed to be in the negative x direction. I didn't do that. So where's my dt? Let's make dt as 100. And then let's increase the rate down here. Let's increase to 5,000. I don't know. Check that out. Okay. Now, that didn't work. It kind of worked. It kind of worked, right? And I kind of like it. And I do know that Lagrange points L1 and 2 are unstable. So what I suspect the problem is that I haven't found the exact location. So I'm really kind of off. I broke that distance of R into 10 to the 5th points, and that may have been a problem. So let's change that in my function up here. 10, let's make it even smaller, 10 to the 5th, which will take longer to calculate, but whatever. Okay, so you'll notice it makes it further before getting out of off thing. Let me try it one more time. 10 million points. Okay, so it keeps going further and further and further before it gets out of things. So I think it's legitimate. I just need to refine the way that I calculate it, but I think I technically did calculate it. I want to go ahead and calculate Lagrange point L2, and then I can make a better function for finding those. But I think things are working, right? They're just not working great. So that's that. Okay, so what do I need to do to find L2? Let's go ahead and make a plot. Let's go back up here and say, make a new function. I'm going to use that left-hand side, right-hand side thing again. But now I'm going to go up here and say, okay, so let's switch back to the paper just to make sure we're on the right page. Get it? Page. Okay, so where's my marker? Here it is. So now we're over here. In this case, the gravitational forces are both going to be in the positive x direction. So that's that. This one is still the same, right? Because it's still this distance plus RL2. This is going to be RL2. So that's still this function still works. This one is going to be this distance, so it's going to be RL2 minus R2. So this is going to be RL2 minus R2, which doesn't really matter because you're squaring it. And that's going to be 2. And then this is going to be equal to, I think all I have to do is change the positive sign for that, because that's still the same. Yeah, so I just need to change that. Okay, so let's go over to the computer. I'm going to take these things off. And then I don't want to make this go for very long, so let's just make this 0 times. That way it won't run. Okay, so we're up here. I want to plot RL2. Can I start RL2 as equal to 0? Well, I could, right? But it clearly has to be greater than R2. And I can't make it equal to R2 because I'm subtracting the two of those. So let's say the starting value for RL2 is equal to, and I'm just guessing here, 1.05 times R2. So I'm not starting at R2, it's a little bit past that, and then I can start increasing it until I get to what I want. So this is going to be, now how far do I go? Let's say while this is less than, I'm just going to pick 1.5 times R2. So I don't know if that's going to be enough or not. Okay. I don't know. Okay, so left-hand side, that's the same. I just need to change this to a plus. Right-hand side, I need to change these to RL2s. Oh, and this is technically minus. I don't think it matters. And then this should be RL2. And then I'm going to plot RL2, 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 RL2. Okay, I think that should work. Let's see if it does. Okay, got something. Okay, so there it does cross. And again, the left-hand side is greater than the right-hand side, so we can just do that. So let's make a new function, L2. I'm going to just copy this because it's going to be very similar. And let's call that L2. And let's call that 2. And then dr is, let's just keep that the same. And then we're going to do this. Our L2 is, and I'm going to say 1.5 times R2. And then we said this was equal to I'm going to put 1.001 times R2, right? Because I can start, I don't really care about graphing it, so I can start as close as I want. It doesn't really matter. This I need to change. I can just copy this stuff. Oops, not too much. No, they didn't do it. Oh, that's not what I want to copy. I want to copy this right here. Tab, tab, RL2, 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 RL2. And let's print that. Print L2 R M1 M2. And let's just see what happens. Okay, so I got 2.45 times 10 to the 10th. Go over here. Looks like it's working. Okay, so now we can go ahead and add in our other mass. I don't need to plot that stuff anymore. So let's just take all this stuff off. Go down here. I'm going to make another ball. It's going to be ball 2, right? Because it's at Lagrange point 2. Ball 2 equals sphere. Oops, got to spell that right. The home row, home keys. Sphere, POS equals vector L2 R M1 M2 0 0. Radius the same. R divided by 60. Make trail equals true. Ball 2.m equals 1,000. That doesn't really matter. I mean, that's that number pales in significance to the other one. Ball 2.p equals ball 2.m times vector 0 negative omega times ball 2.pos.x 0. Okay, so now down here I need to calculate two more vectors. I need R21 is going to be ball 2.pos minus star 1.pos. R22 is ball 2.pos minus star 2.pos. Yeah. Okay, so now I can go down here and calculate two more forces. So F21 equals negative G times M1 times ball 2.m times norm R21 divided by mag R21 squared. F22 equals negative G times M2 times ball 2.m times norm R22 divided by mag R22 squared. Now I need to update the momentum of ball 2 plus F21 plus F22 times dt. Now I need to update the position. Ball 2.pos equals ball 2.pos plus ball 2.p times dt divided by ball 2.m. Boom! And finally, that's it. Okay, let's see if this thing runs. What do you guys think? Do you think it's going to run? Oh, you know, it did. But you remember, I set the time to 0. So up here, let's take out that 0. See, that way I didn't have to delete that number. There you go. Okay, so it looks like L2 is more stable, but it's not perfect either. Okay, I won. Ooh, wow, I got ejected. That's crazy. Huh. I wonder if it'll come back. So I think my next step is to make a better calculation to get a more refined value for those things. Let me just go up here. Let's make this more Earth-like. What if I make this even smaller, 10 to the 28th, and let's make this bigger, 8. Is that better? Now, I just want to emphasize that I am modeling the motion of those things. I'm not animating them. Those are moving with forces and momentum. It's modeled. And it looks like it's much more stable now. So I bet that if I made it Earth-like, it would be better. But I want it to work for everything. I want all Lagrange points to work. And you can see right here, L1 starting to diverge. So there's a lot more cool things to do, but I think that's good. I'm putting this all together in a playlist of Lagrange points. And so you can use that link to see everything. Of course, the code will be down below and my previous video too. So I had fun. It's going to be some more stuff. We still have to do, that's 1 and 2. We need to do 3, 4, and 5. There's more Lagrange points to make. But I want to make, the next thing I'm going to do is make these values more accurate so that it actually stays. It's not a stable orbit. It's not a stable position, but if you put it there exactly, it should stay there. I think it should work a little bit better. Okay, so that's that. I will come back to this and we'll finish